Okay, so why don't we have a look at that? All right, so we've got this projectile A that's going to slide across a flat table, okay? So it's just cutting at an angle across the table. And we've got the friction here, and we've got the mass, and I think you probably want to do some work energy here. And after you do that, I think you'll get the velocity right before it hits, and that is exactly 40 meters per second. So we're good with that. We got any questions on that? Yeah, it's
yeah, nice day on Friday.
Yeah. Anyone else need a copy of this? So we're good with that? Okay, now that's going to embed there, and what's going to happen is you're going to use momentum because that's a collision. So I think you're going to use momentum for the collision. And you're going to do it in the X direction because that channel only goes in the X direction. The Y momentum will be absorbed. So right after the collision, I think we're at 8.66 meters per second. Okay. So any questions on that bit? So the two will be moving together now. Okay, good. Okay, then you got some more work energy in here. So by the time you're right there, and again, this is AB now. And I think what they're doing right before they hit C is they're going at 8.17 meters per second. Okay. So that's basically what's happening right here. So we good with that? Doing all right? All right, so that's when you get into the next bit here. Now with the next bit, what's happening is there's a transition happening there, and that's kind of a transition between the linear momentum of AB and the angular momentum of ABCD. So you need to be able to kind of analyze that, all right? So we could visualize it first, I suppose. And we were looking at this on Friday, or Wednesday, I mean. All right, so there we go. I guess we'll let that run its course and we'll go back to what it was doing. All right. So what's going to happen here is you're going to have AB coming in towards it in a linear fashion, okay? And that's just about to hit is what's happening here. All right, and so that part of the analysis you've done some homework on already, if you remember. And what that is that's like 261, basically. Okay. So 261 is what that's like, and that's on page 14. Okay, so that's like 261. So what you're looking at there is AB, and then you look at the offset of AB from the center point about which things will rotate, and they'll rotate about, for us, I can't remember what I called that point, but that's center point, the point, the pivot is O. Okay, so that'll be the distance from O to that moving projectile. Okay. All right, now once it hits right there, now the whole thing is rotating. So you can't just call that linear momentum of ABC. And the reason you can't is you've got D on the far side and it's rotating too. So as soon as AB hits C, D starts to rotate also. So you've got to account for that. So what you're doing there basically is making a transition from linear momentum to angular momentum. Now what you've got going on there for that part is, again, it's like 261 that you did in the homework, but it's also got a little bit, you've got more than one part that's rotating. Okay, so once that thing hits, you've got two parts that are rotating. So what you're going to have is that's rotating, but this is too, okay? So that's rotating, and so is that. Now when that occurs, what you've got is kind of a combination of 261, but then the fact you've got more than one thing that's rotating puts you in a mode of handling it like, I think it's 263, okay? So those are the things you could be looking at to kind of understand how to analyze this. Okay. Then the last bit is how long it's going to go until it stops. So anyway, are there any questions on that? I don't know if I'm going to get the answers to that, but do you have questions on it? People that were here Friday meeting about the
nice question.
Uh-huh.
So I didn't hear you say anything about it, but do you want us to put this into MATLAB or Excel?
No, and yeah, that handout I gave you, we're just doing the front page. So I just want the time for it to stop. There are some instructions on there about going into MATLAB or Excel, but you don't need to do that.
Okay.
We'll just find the time to stop. All right. So we got questions on that? Other questions regarding this? Now, what's going to happen here is you're going to get the force of friction, and that's just equal to mu Fn for each of the parts, because if you look at that bracket that holds them together, it's up above the ground, or the floor, I guess you'd say, and you can let D and ABC, they'll drag on the floor and there'll be friction caused by only their weight, okay?
In the axis, it spins on in the center, it doesn't have friction.
Yeah, there's no friction at O. The armature too is lifted off the floor, okay? So you can find those frictions. So what's going to happen as this thing spins, given the nature of how it's set up, the friction will always be normal to the axis. So when it's over here, you know, you'll have D right there, and then you'll have ABC here. The friction will still be normal to the motion. Okay, so it's everywhere normal to the motion. So what you get out of the friction there, I guess I wouldn't call it a couple, but it's something like that. It's not a couple because the forces are not equal to each other, but they're always parallel and perpendicular to the motion of the blocks there, of the objects.
Sister forces or something like that.
Yeah, I don't know. I don't know what you'd call them, but all right. So what you're going to want to do then is figure out how long it takes them to stop, and actually, again, that's back on 261. You know, so if you apply the principles that you learned on 261, this is a more complex problem, but it follows along 261 quite a bit, and the fact that there's two objects there. Kind of, when you look at 263, that would get you an idea of how to handle that. Now, the last little bit on this thing is that the whole thing moves as a unit. Now, there's nothing really, you know, super tricky on this in that regard, except that you'll notice that ABC is it's further from that center pivot, so it moves faster than D. Okay, it's got a higher V, a higher velocity. So you know, some of you were pointing out that ABC will not have the same velocity as D, so that gets you two unknowns in the angular momentum equation. But the deal with this is that you don't do anything real tricky to do that. You just use the angular momentum equation, but you got to find a way to get those two variables, VABC and V sub D, just broken down into one, because you're going to only solve for one unknown in that equation. So you're going to have to get it down to one unknown, not two. You can't solve it if you call it those velocities VABC and V sub D. They you can't work it out if you leave them in that form. You've got to find a different form to put them into the equation to solve. Okay. So, we got any questions regarding this thing? This is due Monday. It's just a homework problem. I just want to know the time for it to stop, which it ought to be somewhere between 1 and 2 seconds. I'll tell you that. Okay. So what I'd like you to turn in would be that front sheet with the answers filled in there, and then also the work that you did to get the answers. Okay. So we good? You got any questions? Yeah.
So just to clarify, so from A to B there's friction once it's rotating, but just in the channel from B to C is when there's no friction?
No, there is friction in that channel from B to C, just not on the walls. It's all on the floor. So you're just doing force of friction is mu Fn from B to C. You know, you don't have to worry about anything going on the walls.
What if there was friction on the walls? How would you do that?
I don't know. Yeah, I don't really know how to get a normal, you know, for a normal on a floor, it's pretty straight up. You just find components of weight and, you know, work that out. But on a wall, it's harder to do that. I don't really know how to analyze something like that because I can't really come up with a consistent normal when I think about it. Mm-hmm. So off the top of my head, I don't have a good way to do it. Other questions? We good? Okay, so that's the only thing that's due Monday is that one. So let's have a look at plane motion now. So we did all that vector stuff for rotation. Let's kind of apply it here and see what we can come up with. I'm on mostly 520. We might look back at 506 also a little bit. I don't know. We'll see. So let's look at motion in a plane. So if that bicycle's pedaling across the ground there or the road, you see an internal combustion there in the middle, an oil derrick over there on the right. All those things have certain types of motion that we can analyze with some of the stuff we're going to look at here. So let's see what we got. Yeah, this is on 506. This is getting back to that relative motion. So if you want to analyze plane motion, what you can do is break it into two parts. A translation is the movement, generally speaking, of the center of gravity as the object moves. Okay, so that's just a nice smooth, maybe not linear, it might be kind of a curve, but some sort of motion like that, okay? A fairly straightforward motion. If the whole object were a particle, that would be the motion of the particle. Now, when you get into objects that have dimension, though, you also have to add in how the object rotates as it translates, okay? So it's going to do both at once. So rather than trying to analyze all that stuff in one equation or one approach, normally the way we do it is we break those two down into two things and then add up the net effects of them, okay? So that's generally how we analyze that. So if you think of throwing an object across the room or something, a stick or something like that, and spinning it, the way you'd analyze that is you just add those two motions together. The translation of pretty much the center of gravity for that object, and then add in how the object rotates about its center of gravity. And you can constrain the object such that it doesn't have to be rotating about its center of gravity. If you start looking at the linkages on those oil derricks or the connecting rods on the pistons or whatever, you can make something rotate about a point other than its center of gravity. But the net way of analyzing is pretty much the same. You start with a translation of a point, then look at how the object rotates about that point, okay? So that's how we do that. So let's have a look at a special case, a wheel that rolls without slipping, and this is on 520. So this is where we'll start analyzing stuff. So generally speaking, wheels roll without slipping. So that bicycle, unless you're skidding or something like that, those wheels will roll without slipping. Certainly that big semi-truck, generally speaking, the wheels roll without slipping. And when a wheel rolls without slipping, it means there's a direct connection to the rotation of the wheel and the translation of the object that the wheel is attached to. So if the wheel of the truck rolls without slipping, the velocity of the truck is related to the rotational speed of the wheel. There's a direct relation there. Now, if you break that relation some way, the wheel slips. So these are things we're not talking about. Okay, common case of that is when you're on the ice, your wheel's spinning very fast, but your car's not moving much. Okay, so that means the wheel's slipping. There's not a good relationship between the velocity of the wheel and the velocity of your car. Same thing here, if you jump on the brakes, you can move the car without the wheel moving much at all when you skid, okay? So those are two examples there of wheels that don't roll without slipping. But we're going to concern ourselves with the more even motion of wheels that do roll without slipping, okay? All right, now let's have a look at that. So let's say we've got a wheel, and I'm on 520 there. And let's say that wheel rolls without slipping. Let's look at the relationships between how quickly the object it's attached to, the bicycle or the car or whatever that happens to be, how it moves versus how the wheel spins. What's going to happen here if you rotate that wheel from A to B, so if that wheel rotates such that A comes down there to the bottom, you're going to have this arc distance. This arc distance will be the distance that the vehicle travels. Okay, and that's the relationship there. For every meter of arc distance that the wheel rotates, the vehicle will move a meter, okay? Now my sketch is a little bit out of scale, and I had to do that to get the wheels separated there, so I could draw it. But the idea here is that the linear distance from O to O prime, where the axle starts and where it ends up, that will equal the arc distance from A to B, okay? And we'll call that S. Okay. So the velocity of whatever the wheel's attached to, let's say it's a bicycle, the velocity of the bicycle we'll call V0, and that's that arc distance over the time. Okay. Now, as the thing rotates, there's a certain angle that it rotates, and we'll call that theta. Okay, what theta is the proportion of the arc distance divided by the circumference of that wheel, the distance around it. All right, that's a proportion of the circle that this arc takes up. And then if you multiply it by the circumference, you'll get that distance. Okay, we'll get the angle in radians is what we'll get. Okay, so what we're doing there is we're saying that we're taking up a proportion of the circle that's equal to S, the arc distance, divided by 2 pi r, the circumference. And then we've got 2 pi radians in a circle, so S over r, when we cancel out the pi and the 2, that gets us the angle in radians. Okay. So that's the arc distance, which is also the distance the bicycle's moving, divided by the radius. That'll get us that angle in radians. Okay. Now the angular speed is that angle theta over the time, so that's S over RT. Okay. So there's the angular speed. All right. Now, if we look at the, so what we got here is the velocity of the bicycle is S over T. To accomplish that, the angular speed of the wheel is S over RT. Okay. Now, if we look at just the wheel itself without it translating across the ground, but if you just look at how the wheel rotates, the velocity of a point on the perimeter of the wheel, as that thing rotates like so, that rotational velocity will be omega S over RT times the radius of the wheel, which is r. So what we get there is the velocity of a point on the wheel simply due to the fact it's rotating. Its rotational velocity is v0 also. All right. So that was a little bit of a speech there involving lots of V's and S's and such, but let's kind of boil this down so we understand this. If I'm on a bicycle and I'm pedaling it and the wheel doesn't slip, the velocity of the bike, S over T, is going to equal the velocity of a point on the perimeter of the wheel simply due to the fact it's rotating. They're equal. Okay? And they're both equal to S over T. So what that means, if I really zoom in and look at that wheel, I've got a situation like that, where the entire bicycle, including the wheel, is moving to the right with a velocity equal to v0, like so. Okay? But as that happens, the wheel's rotating also with an equal velocity of v0. So the perimeter of the wheel's doing this, rotating clockwise with that v0 velocity on the perimeter. So if I want to know the velocity of any point on that wheel, what I call the absolute velocity, I got to start adding vectors together. Okay. So if I want to know the velocity of the center of the wheel, the axle, well, that's pretty easy. That's just the velocity of the bicycle itself. If I want to know the velocity of a point on the top of the wheel, it's actually 2 times v0. Because it is moving with the bicycle, it's translating with the bike with v0, but on account of the fact the wheel's rotating, I got another v0 up there. So the net velocity of that top point is 2v0. Okay? a point at the bottom has a net velocity of 0. Okay? Because it's translating to the right with v0, but it's rotating to the left with v0, and those two cancel out. Okay? So what you can start doing is looking at a wheel that rolls without slipping and looking at specific points on it and figuring out the absolute velocity of those points. Okay? So we doing all right with that? Kind of a key thing to kind of understand because we're going to use this a little bit. Okay? And I just made this one up. I don't think I've got this on page 520, but I got some room down at the bottom maybe to put it. So let's say we got this car going at 3 meters per second. If I want to know the velocity of these points, what I'm going to do is what I just did. I'm going to take that velocity and apply it in two different ways, okay? So every point on the wheel and every point on the car is moving to the right at 3 meters per second, okay? But as that's happening, the wheel's rotating, okay? So what's going to happen as it rotates, it's going to rotate clockwise, and it rotates with an equal velocity. So that point's going to be moving down at 3 meters per second as it's going clockwise. B is going to be moving to the left at 3 meters per second. D is going to be moving to the right at 3 meters per second. O will not be doing any of those because it's not on the perimeter, it's right in the middle. Okay. So once I can see that, and I've got that figured out in my mind, I can come up with the velocity of any point I want now, see? What's the velocity of O? That's pretty straight up, eh? It's the velocity of D. It'll be 3 and 3 more, okay? It'll be 6. Velocity of B zeroes out down there. Just for that one instant, it sticks. That's why it doesn't slip, see? It's sticking down there for just one instant. Yeah, question?
So when a car's, if you did lose traction and it did start slipping, one of the lower 3 speeds is different then in that case?
If the car, if it starts slipping,
Yes.
what's going to happen are the rotational vectors that I've drawn in red, they're going to change.
Yeah.
They'll all be equal, but they'll change, and they won't equal 3 anymore.
Yeah.
And if it's on ice, they'll be greater than 3. If it's skidding, if you're jamming on the brakes and skidding, they'll be less than 3. Yeah. So this whole set of relationships will get thrown off. How about A? What's the velocity of that? Yeah, square root of 18. Is that 242? Maybe, maybe not. Okay.
Close.
All right. Well, you'll give it to me? All right. Good. Okay. So that's just a fact to know about wheels that roll without slipping. And dynamics books seem to just love wheels that roll without slipping. So you want to remember this one, okay? And just remember that the velocity of the vehicle the wheel's attached to equals the velocity of the point on the perimeter, the outside of the wheel due to rotation, okay? That's just how it works, okay? So there we go, all right? All right, now we can apply this to doing some different things. This concept, we'll use this later, but this is also a pretty straight up example of relative velocity. Because what we're doing there to find the velocity of d is we're taking the velocity of O, which is the translation, plus the velocity of d with respect to O, which is a rotation, okay? And let's see. When I change that to A, just because it will just serve me a little bit better to write out the vector, I'm sorry, but it'll just be a little easier for me. Okay, so the absolute velocity of A equals the velocity of O, which is a translation. So that's a translation there. That's just how how the car itself or the bicycle or whatever is moving across the ground. And then the velocity of A with respect to O is a rotation. Okay? So that's how I'm looking at that. So you can see that translational velocity is 3I and the rotational velocity is minus 3J. Okay? And you can combine them together to get the absolute velocity of A. That's the idea, all right? So we're doing relative motion there. So the plane motion, the absolute, whatever you want to call it, absolute motion, is the translation plus the rotation. And we've got the means to calculate that stuff, you know. We can do the rotations either geometrically or we can take omega crossed with r, and I forgot my little vector hats there, but that's what we got, all right? I don't know if I put that on 506 or not. The sketch is in 506. Yeah, I've got the words in there too. I don't have the symbols, but I've got the words. All right, so that's the basics on wheels. Now we can analyze stuff other than wheels too. We can look at, we'll start with some simple machines here. Maybe an internal combustion engine or an oil derrick. Let's see what we can do with that. Let's see what we can do with this set of linkages. I'm on 540. Let's figure out what the velocity is of C, which is a collar that moves vertically on that shaft. And what we got is we've got the linkage from A to B. We got its length and angle. And then we've got the angular speed of B, or excuse me, of AB. And then we've got the length and angle from B to C. And we've got the fact that collar travels on a vertical rod. So let's see what we can do with this, okay? All right, so the first is we're going to start at what we know, and what we know is the velocity of A is 0, okay? Because that's a pin joint. You all remember that from statics, that symbol? That means A isn't going anywhere, but it can rotate, okay? So if B is rotating about A, what we know is that the velocity vector, VB, is perpendicular to the radius, which is represented by AB. So if we know that, we can figure out the direction of VB, can't we? Because that'll be 34, and that'll be 56, which is 90 minus 34. So if B is rotating about A at this instant that we're analyzing it, the angle in there is 56, up and to the right. Okay. So what we can do next, if we know that angle, is we can find the magnitude of the velocity. because we got the angular speed, that's 6 radians per second, and we've got the length, 0.46 meters. So 6 times 0.46 is 2.76 meters per second. So that's the speed of B. And we can also, we know the direction, it's upright at 56. Okay. So I can vectorize that. Cosine 56, 2.76i, sine 56, 2.76j. So I can get VB into a vector form, 1.54i plus 2.29j. Okay. So being as I know B is rotating about A, and I've got the angles and the lengths and all that, I can work through the geometry there and find a vector expression for the velocity of B. So now I know VB. So I've worked my way from A to B. Now I'm going to go from B to C. See, I know the velocity of point B. I found it by analyzing AB, but I can use it on the linkage BC. B is part of 2 linkages, AB and BC. Once I found the velocity of B, I could use it on either linkage. Now I'm going to go on to BC. All right, now what I'm going to do, I'm going to use a relative velocity equation. I'm going to use VC is VB plus VC with respect to B. And I know what VB is now. So I got to figure out some stuff about VC with respect to B. Now why don't we have a look at what C is doing with respect to B so we can figure some stuff out here, okay? And to do that, maybe we'll go to a little bit different model, but the same sort of idea. So why don't we go to an internal combustion engine here, okay? Now, I think it used to be people did a lot more working on their cars than they do these days, but there's this working model program put together by someone who knew what they were doing a little bit, more than I do. So they came up with a piston, a connecting rod, and a little lobe on the camshaft there, okay? And they're coming up with how that would move, okay? So this is similar to what we got because they've got a rotation of the, not camshaft, crankshaft there. Okay, rotation of the crankshaft. They've got a connecting rod, which rotates, which acts there, and then they've also got a piston, which is in a linear vertical motion, kind of like our collar is. So that's not exactly the same setup as we've got, but it's pretty darn close. You could think of this offset on the crankshaft here as being like another linkage. Then we've got, so linkage number 1, linkage number 2, and a vertical motion, very similar to what we got, okay? Now, that's what came with my working model program. And I worked very hard to, let's see, recreate that. So what did I come up with? I came up with that.
Relative motion taken about the bottom of the connecting rod where it connects to the crankshaft.
I don't want that one. Okay, let's get out of there. Let's go to this one. Open with, there we go. All right, so here we go. There's my simple model of what you just saw. So we got a rotating crankshaft down here, and then we've got a connecting rod and the piston moving vertically. Okay, same idea. All right, now what I want to know here is what's the motion of the piston with respect to the point on the crankshaft there, right there, okay? And I know that's a little fuzzy there, but right here, what's the piston doing with respect to this point? So what I mean by that is if this is like a carnival ride and I'm on that point there and I look at that piston, what's the piston appear to be doing from my moving perspective? Not moving? I think it is moving because the angle of the connecting rod changes as that thing rotates. So if nothing else, it's going to be doing that. It's going to be moving left to right, okay, from my perspective. But the other thing is it's got a solid piece of metal connecting where I am to the piston that is a certain length. So if that piston is going left, right from my perspective, but it's always that same distance away from me, because I'm moving too, what does the piston now appear to be doing? Left, right, same distance away. Shall we have a look at working model? Okay, we're going left, right, and we're always the same distance away. So what that looks like is, suspense is getting to be
Relative
here.
motion taken about the
So
bottom
what
of the
I've done,
connecting
what I'm
rod where it
doing
connects to
here
the crankshaft.
is I've got the same model, but I put my point of view at the end of the crankshaft down there. You can do that with this program. So that's getting me a relative position there on the end of the crankshaft, and it's going to show what's happening from that moving perspective. So have a look at what the piston does with respect to this point. Okay. So what's going on there is the piston is always the same distance away from that point, and it's moving to the left and right, and that's an arc, is what that is. So from the point of view of this end of the connecting rod, the piston's rotating about it. That's what relative motion looks like for 2 points on the same object. One point is rotating with respect to the other. Okay? So that's relative motion, not absolute motion, that's relative from the moving perspective of the end of the connecting rod. Okay? We got any questions on that bit? Okay. So if we come back to our example, from the perspective of here at point B, what C is doing is rotating about it. Now that's obviously not the absolute true motion of C. What C's doing actually is moving up and down on that vertical rod. But from the perspective of B, it's rotating. And if it's rotating, it's perpendicular to the radius. Okay? So if we have this rotation here, that's going to be a perpendicular. Okay, so that's the relative velocity of C with respect to B. So the magnitude of that velocity is going to be 0.6 omega, because the radius, the linkage length, is 0.6. And I don't know what omega is yet, but I know that the velocity, the magnitude, that speed is 0.6 omega. You all good with that? A little bit abstract here because we're talking about relative motion from the perspective of B, looking at what C's doing. Okay. So omega is an unknown, but I can work through that. That's okay. Now what I know is that velocity is perpendicular to the linkage. The linkage makes up a 17-degree angle with the horizontal. By parallel angles, that's 17 also. So VC with respect to B is 90 degrees, okay? Because C is rotating about B, so it makes that relative velocity makes a 90-degree angle with the linkage. So if I take away the 17 degrees from the 90, I get a 73 for the relative velocity, up left, as I have assumed. So that vector expression for VC with respect to B is minus 0.6 omega cosine 73I, minus because it's to the left, and plus 0.6 omega sine 73, positive because it's up. And so that's the I and the J components. And then I can do the calculations and get down to this expression right there. So that's the relative motion. of C with respect to B. Okay. Now, be a little careful when you write this expression because you've got to be sure it matches reality. That relative velocity can be up left. It could also be down right. If it's down right, the right would get me a positive, the down would get me a negative. So I could write that expression up as negative 0.6 omega cosine 73I plus 0.6 omega sine 73j, or I could write it up as positive 0.6 omega cosine 73I minus 0.6 omega 73j. I could write it up either way, but I cannot write it up with the signs switched from those two. I can't write it up as a plus plus because it's not doing that, nor can I write it up as a minus minus. Those are illegal. I can't do that because plus plus assumes it's doing that, minus minus assumes it's doing that. It's not doing either of them. So you got to be sure you get the right sign combination when you write these expressions up. The sign combination has to represent something that could actually be occurring. Okay, as that relative motion includes a rotation. Okay. So I've got a possibility there with my unknown omega. And now that I've got that, I can throw all this stuff into a big old vector equation. So what I've got for my vector equation is I've got 0I plus VCJ, that's VC. The reason I write it up that way is VC is on this vertical rod. It's moving up and down. It only has a J component. So the absolute velocity of C is 0I plus something J. I know that because the C is on a rod. Okay. Then I've got the velocity of B, and I've already figured that out when I did my little analysis there on linkage AB. Okay. So that's VB there, and I already got that figured out. And then I put in my expression with the proper sign combination for VB with respect, or excuse me, C with respect to B. Okay. And then I got everything in one big old vector equation. And then remember, that's a 2D vector equation, so that's really two unknowns, or two equations wrapped into one, you might say. So I can pull the x equation out, the I equation, and I'll have 0 is 1.54 minus 0.175 omega. Okay. I can solve for omega then, that's the rotational speed of the linkage. That's a positive 8.8. Okay, so I assumed correctly with my signs of negative and positive. So my answer came out positive, 8.8. Then I take that and plug it into the J equation, which is VC. Is equal to 2.29 plus 0.574 times omega, which is 8.8. I'll get the velocity of C. Okay. So what's happening right now in that particular configuration is C is moving upward at 7.34 meters per second at that instant there. Doing all right with that? Okay. So that's how that goes. Now, if you guess wrong in your directions for the relative velocity, if I'd have used a plus minus instead of a minus plus, I just would have got a negative answer here. And it's no problem at all. You just take the negative answer and plug it in and everything comes out. So whatever you get out of it, you get, and just plug it into the next step. Don't worry about assuming right or not. You could go up left or down right. Either one of those assumptions is good. Up right and down left or not, though. That'll blow up on you and you won't get the right answer if you do that, okay? Okay. go. I think this is the 16th of May, I think, when this is due. I think Wednesday's the 16th. Okay.
291.
Yeah, 291. Okay. Hope you all have a good weekend.